In this video, we'll be trying a few numericals associated, or probably just a single as per the time permits. We'll be trying a numerical associated with the Newton's laws of motion, and while discussing the theory, a bit of theory and a related example, we'll be knowing about the various aspects of the laws of motion. Now, let us consider the connected motion. In case of connected motion or contact motion, we have objects to be kept in contact with one another. Suppose we have three objects, different masses. We have a mass m1, we have a mass m2, and we have a mass m3 to be connected to one another, to be in contact with one another, and we are applying a certain external force from one end. Now, as we apply a certain external force, it is sufficient, and obviously it is unbalanced because there is no balancing force from the other end. From the other end, that is from the right side towards the left, you have a force, external force acting from left to right on the system of connected bodies, but obviously no other force on to the on applied from the right hand side to the left hand side on M3. Had there been a force acting on along that line, and had that been of equal magnitude of that of the external force applied on the left hand side, then the forces would have balanced each other like this. Suppose if I consider a single body where I'm applying a force from one end and the other force from the other end, and let this be F1, let this be F2, and if F1 and F2 have equal magnitude, then obviously there will be no net motion of that object because the forces will be balancing one another. Now remember, these are two individual forces acting on a single body. But in case of action and reaction forces, it's not the same thing. When you are applying a certain force of action on a particular body, that body applies a reaction force onto the other body which was applying the action to it. Okay, we'll be discussing that as we discuss this topic. Now moving over to the figure onto the left, let this system, as a result of the external force, accelerate onto the right hand side, that is along the direction of the external force applied at an acceleration rate a. Now these objects remaining in contact with one another will definitely apply force, like in case of F external acting on M1. M1 further will apply a certain force internally on M2. Likewise, M2 will apply a certain force on M3, but that's not all. M2, as a result of the force from M1, will give back the same amount of force but in opposite direction, following the Newton's third law, which states that to every action there is an equal and opposite reaction. And similarly, M3 experiencing a force from M2 will apply a similar force but in opposite direction, obviously on M2, and that is the reaction force. Let me denote that. Suppose I denote FAB as the force on A due to B, then here I can say the force on M2 due to M1 is simply F21. And similarly, the force on the third mass, that is M3, due to M2 is simply F32, F force on 3 due to 2. And likewise, the reaction forces can be given as F on 1 due to 2, and F on 2 due to 3. And now remember that F21 is equal to the magnitude F12, but they are oppositely directed, that they being action and reaction forces. And as you can see, F21 is acting from M1 over M2. M2 is applying a certain force on M1 and not on itself. So the action and reaction forces are acting on two different bodies. The first one, the action from M1 over to M2, and the reaction from M2 over to M1. Now, one may question that what about the external force? The external force is being applied by a certain object on M1, and so M1 will be applying a reaction force exactly similar to that object, but we are not concerned about that object. We are concerned about this three mass system. Now, the case where we also have F32 to be equal to F23 in terms of the magnitude. So taking these cases into account, we can now move over to the free body diagram. Now the free body diagram involves that we consider one object at a time. Now suppose we have the mass m1 over here, and what are the forces experienced by it? The external force is acting on it directly, and an internal reaction force from the mass m2 over to it is acting in the opposite direction, that is F12, as shown in the figure above. There is no other force acting on M1 directly. So M1, under the influence of these forces, is getting accelerated towards the right hand side, that is along the direction of F external. So obviously F external is greater than F12, that is the reaction force that it experiences. So that means the equation over here can simply be the forces. Now when you are involving vectors, you always add them to find a resultant, to obtain a resultant, and they result in a vector which is m1 times of a. But vectorially, if we are but in terms of magnitude, if we consider this, these F external and F12 are exactly in opposite directions. That means the angle between them is 90 degrees. And what about the addition rule of vectors? In that case, we have F external squared plus F12 squared plus 2 times of F external multiplied with F12 cos of 180 degrees, because the angle between them is 180 degrees. So this gives me the resultant force between two vectors, and obviously cos 180 is -1. So you are left with F external squared plus F12 squared minus 2 times of F external into F12 taken under root. This simply is F external minus F12 whole squared under root, and that is obviously equal to the magnitude of F external minus the magnitude of F12. So this is the magnitude of the forces that are involved. So if I take this magnitude and keep this in the form of magnitude as well, then what I have is, I write m1 once again for a clear view of it. So m1 times of a magnitude wise, and the magnitude over here is simply F external. We can consider the magnitude because we are observing a linear motion or a straight line motion, in this case a horizontal line of motion, so there's no problem with that. So this is the first equation that we can consider, that is F external minus F12 is simply equal to m1 times of a. Now consider the case of the second body, that is the mass m2. Now m2 again is experiencing two forces. M2 over here is experiencing an action from the first body M1 and a reaction from the third body. As a result of that, it is accelerating along the line of F21. So that means F21 is greater. And again, considering the magnitude, the addition of vectors result in F21 minus F23 equals M2 times of A. This is the second equation. Now considering the third equation, we have the mass M3. And what are the forces involved on that? Now the force acting on it is simply F32, the action that is provided by the second mass over to it. And the acceleration is along the direction of the force, so there's no problem with that. And we have the third equation as F32 to be simply equal to M3 times of A. And this is the third equation. Now adding all these equations that we have obtained, if we add them up, what do we have with us? F32 and F23 being equal in magnitude, you have a minus sign over here and a plus sign over here, so they can cancel out while adding them. F12 and F21, while adding equations 1, 2 and 3, they can get cancelled out as well, and all that we are left with is the external force, which is completely responsible for the motion of this system of three masses in contact. The acceleration being common in each case, we can take the masses and add them up. So we have the total mass of the system, which is m1 plus m2 plus m3, and that multiplied with acceleration gives the magnitude of the external force that is being applied. And from that we can also determine the other way around, the magnitude of the acceleration, that is the external force upon the total mass of the system. Simplified case, if this force supposedly was acting along a different line, that is to say that if we had the force to be acting along a certain line like this, making a certain angle with respect to the horizontal, then we would have had the line of action will be some angle theta, and as a result of that you will have a cosine component of the force to be acting along this direction. So that will be the reason why it will be moving along the horizontal line with a certain acceleration. So if this mass is m, so you have now F cos theta to be responsible for the horizontal motion with an acceleration a, and you must be having some F sine theta, but that is for the vertical motion, if at all any in this case. But this is simply for the horizontal motion. The vertical motion can be dealt with in case of friction and other gravitational motion, if is the case on that occasion. Now let me provide you with a question that you may try in order to find the clarity of your concept. Now in the above case that I've just discussed, that is this one, I would like you to try a question where suppose we have the masses. I'm writing the question over here. Suppose the masses that have been provided in this particular system that we have over here, that is this figure, masses m1 being equals to 2 kg, m2 equals to 3 kg, and m3 equal to 5 kg. If we have these masses and we have the force F21, that is the force that is acting on 2 due to 1, F21 is simply equal to 16 newtons. Then try finding out the acceleration and the other forces that are involved. That is the external force F32, F23, F12, likewise. So you have one of the forces and you need to find the acceleration of the system and the other four forces, that is external force along with F32, F23, F12. Try solving that and check for yourself if you have a clarity of concept from this video. We'll definitely discuss this numerical in the upcoming video for you. Till then, thank you for watching.